We are students from University Tunku Abdul Rahman, and we are here to present our capstone project titled Production of Glycerol Carbonate. So without further ado, let me introduce our members. So my name is Chua Jet.
And my name is Lau Tabi.
And my name is Song Ho Chuan. My name is Eugene.
The objective of the project is to provide a learning experience for the student upon a range of knowledge and skills developed throughout the course, including plant design and synthesis, that incorporate concepts of sustainability, environmental, and safety, reporting skills, both written and oral. It is also to provide a test of the student's capacity for independence of thought and judgment. From this project, there are 3 learning outcomes that we must achieve. First, to integrate and apply all the technical knowledge learned throughout the course. Second, to combine the concepts of sustainability, environmental, and safety in a holistic approach. And third, to present and defend the design in the form of oral and poster presentation. So in this chapter 1, I'll be talking about literature review and project conception. So under this topic, I'll be talking about process background, market survey and site study, as well as process selection. Glycerol is a byproduct from biodiesel production, in which for every 10 kg of biodiesel produced, 1 kg of glycerol is produced. The growing industry of biodiesel also led to the excess of glycerol stock. An estimated feedstock of biodiesel will reach 37 billion gallons in 2016, with 4 gallons of crude glycerol. As such, selling price of glycerol has been reduced to 2.5 to 5 cents per pound. Because of the excessive feedstock, various attempts has been made to reduce the feedstock, including disposal. Various methods for disposal and utilization of this crude glycerol has been attempted, including combustions, composting, anaerobic digestions, animal feeds, and thermochemical biological conversion to value-added products. However, such method is deemed not economical, leading to the research on conversion of glycerol to a more useful product. Previous attempts on glycerol conversion includes 1,3-propanediol, epichlorohydrin, acrolein, glycerol carbonate, and glycidol. Most of the glycerol produced from biodiesel production is full of impurities. Therefore, it can be called crude glycerol. Crude glycerol generated from biodiesel production is impure, and in general, glycerol makes up of 65% to 85% weight content of the crude stream. Methanol and free fatty acids are the 2 major impurities contained in the crude glycerol. The existence of methanol is due to the fact that biodiesel producers use excess methanol to drive the chemical trans-esterification to complete, and do not recover the entire methanol. The soaps, which are soluble in the glycerol layer, originate from a reaction between the free fatty acids present in the initial feedstock and the catalyst. Dimethyl carbonate, or DMC, is a versatile, non-toxic, biodegradable reagent with chemical reactivity that is alterable, which can serve as a green alternative to dimethyl sulfate, or methyl halides and phosgene for methylation and carboxylation reaction. DMC can be prepared by the base catalyzed reaction between carbon dioxide and methanol. This compound has found use as a methylation agent and more recently as a solvent that is exempt from the restriction placed on most volatile organic compounds in the US. In the early stage of glycerol carbonate production, carbon monoxide or phosgene with metallic catalyst is utilized, in which environmental issue was brought up due to toxicity of phosgene. As such, a safer way to produce glycerol carbonate is developed by reducing the reaction temperature using trans-esterification of glycerol monomer with alkaline carbonate. Ethylene carbonate was initially used together with glycerol to produce glycerol carbonate, but the byproduct, ethylene glycol, which has similar boiling point with glycerol carbonate, makes the separation of both products difficult. Thus, an alternative way of using dimethyl carbonate instead is developed, with the long reaction time being the main issue. Glycerol carbonate itself is a very profitable product, in which the selling price can go up to $8,141 per ton. However, a major setback of production of glycerol carbonate is the high cost of production. Hence, the use of glycerol carbonate is very limited. Despite that, Focus are given to cheaper production of glycerol carbonate due to its usage in various profitable fields, including chemical industry as liquid membrane in gas separation, surfactant and detergent, pharmaceutical industry as solvent, building and construction industry as cement curing agent, agricultural industry as agent for plant activating, and cosmetic injuries as wetting agent. From the source of market, the price of glycerol carbonate is high as it is not produced commercially. Currently, the price of glycerol carbonate was $136 per kilogram with purity more than 90%. However, industrial attention for glycerol carbonate is increasing due to its physical properties and also its reactivity. An important decision must be made before the construction of the plant, which is site selection. The plant should be located at the area which the projected production can be carried out under optimal condition. Besides, the investment for the project should be carried out with the best monetary return, where the production cost is minimized. There are several general factors of selecting a suitable land for a new plant, which is the first, availability of raw material, second, the export routes, third, the facilities and transportation, fourth, the availability of utilities, fifth, labor consideration, and sixth, local community consideration. The ideal site chosen after surveying is located at Carrick Island, 42960 Kuala Langat, Selangor Darul Ehsan, Malaysia. The preliminary decision is to construct a glycerol carbonate plant at an empty field nearby Sime Darby Biodiesel Sdn Bhd, as shown in the figure. The main reason of choosing this area is the accessibility of the feedstock crude glycerol. This is because crude glycerol can be easily dealt and purchased with Sime Darby Biodiesel Sdn Bhd, which is a biodiesel plant that also located at Carrick Island. Another criteria of choosing this site is the importation of materials and also exportation and shipment of products. Port Klang is a town and the main gateway by the sea into Malaysia. It is also the largest port in Malaysia, which can categorize into three ports: South Port, North Port, and West Port. There is a great advantage by choosing the site nearby to a port in order to decrease the transportation and other related fees. Another feedstock, dimethyl carbonate, has to be imported from overseas market since there is no market in Malaysia. Therefore, the transportation fees can be reduced when transport the materials from the port to the plant and vice versa. From the map, the distance between targeted land and Port Klang is about 27 km. The distance between targeted land and the nearest airport, Sultan Abdul Aziz Shah Airport, is about 45 minutes. This airport serves both the domestic and international flights, which may help in reception of clients and attraction of business from other countries. In plant design, cooling piping system is the primary concern in every operation. Water has to be drawn into pipeline and flow to following parts to lower the temperature of the process. Geographically, location of targeted land is near to sea, which means that any general usage of water in plant will be convenient. This brings the advantage of the water drawing, and thus the cost of the pipeline system can be reduced. Industrial site that has been chosen for the new plant in Carrick Island is not too near nor too far from the residential area. The environment of community could be secure, yet also not affecting labor daily working. It takes around 30 minutes to the nearest hospital if any accident happens. Furthermore, Urban City in Carrick Island is about 20 minutes from the targeted plant, which is convenient for employee to seek for lunch during meal period. Besides, canteen can be built in the plant to provide multiple choices for the employee when having lunch. The following slides shows the physical and chemical properties of glycerol carbonate, methanol, dimethyl carbonate, crude glycerol, calcium oxide, carbon dioxide, oxygen, phosgene, urea, ammonia, glycerol, hydrochloric acid, and lastly, carbon monoxide. Transesterification of alkyl carbonate is a reaction of glycerol and dimethyl carbonate, producing glycerol carbonate and methanol. Transesterification of dialkyl carbonate are the most convenient way to produce glycerol carbonate because dimethyl carbonate is a low toxicity chemical and thus having low environmental impact. In addition, this process can be operated in milder condition without the formation of undesirable products such as isocyanic acid and burette that are formed in glycerolysis. Besides, high yield and high conversion can be achieved by using basic catalysts such as calcium oxide. Besides, there are several alternative routes such as phosgenation, carboxylation and oxidation carboxylation, glycerolysis, as well as transesterification of alkyl carbonate. The material market price is listed in the following slides, which includes crude glycerin for food grade, crude glycerin for industrial grade, dimethyl carbonate, uncoated urea, carbon dioxide, oxygen, liquid ammonia, glycerol carbonate, ethylene glycol, and methanol.
So in this chapter 2, I will be talking about process synthesis of process flow diagram. So under this chapter, I will be talking about first process database, secondly, process synthesis approaches and heuristic, and thirdly, the development of base case, flowsheet, and plant layout.
By using the raw material of glycerol and DMC, transesterification can occur by using different catalysts. Among of them are silicate catalyst, magnesium lanthanum mixed oxide catalyst, calcium oxide catalyst, uncalcium calcium oxide catalyst, and under it consists of microwave assisted transesterification and conventional transesterification, zeolite, as well as non-catalytic supercritical DMC esterification. After the transesterification process, the product stream will contain the product, excess DMC, impurities from the feed stream, as well as impurities produced from the reaction. There should be no glycerol remain in the product stream, since the glycerol will be fully converted to glycerol carbonate, given that DMC is put in excess. The effluent of the reactor will be sent to the separator, such as flash pressure vessel, where glycerol carbonate as a product will be separated from the impurities. In the separator inlet will be heated. The heat is directed from the furnace to further heat the DMC up to the boiling point, so that DMC will be evaporated promptly after entering the separator. The impurities will leave the separator as a waste stream, while glycerol carbonate will exit the separator as the end product stream. At waste stream, DMC is further separated from the impurities through another separator. No further heating is required as DMC at this point exists as gas phase, while impurities are either solid or liquid. The DMC will be separated and recycled back to the feed stream, while impurities are removed. At the end product stream, glycerol carbonate is further purified by separator, and any impurities found at this stage is removed and disposed, together with impurities separated from the first reactor. Silicate is a cheap and effective heterogeneous base catalyst. By using silicate catalyst for transesterification process, the optimal condition of calcination temperature is 200 degrees Celsius. The calcination temperature is lower compared to using magnesium lanthanum mixed catalyst. The glycerol conversion by using silicate catalyst can achieve 97.8%, and the glycerol carbonate yield is 95.5%. Other than that, calcined sodium silicate as a non-toxic solid base catalyst has the advantage of low cost, high catalytic activity, and easy reusability. The reaction time of using sodium silicate catalyst is about 2.5 hours, which is longer compared to other catalysts, so the sodium silicate catalyst will not be selected. Magnesium lanthanum mixed oxide catalyst is not selected because of its low surface area. Although magnesium lanthanum mixed oxide catalyst is the strongest basic metal oxide and higher glycerol conversion, but its low surface area will affect its activity as a heterogeneous base catalyst. The other reason is calcination temperature for transesterification process by using magnesium lanthanum oxide catalyst is higher compared to other catalysts. The calcination temperature for magnesium lanthanum oxide catalyst is about 650 degrees Celsius to 720 degrees Celsius. Non-catalytic supercritical dimethyl carbonate esterification of glycerol is not chosen because of its parameter. High pressure must be maintained throughout the reaction to maintain the supercritical dimethyl carbonate. This high pressure applied throughout the reaction has high energy consumption, thus lead to high cost consumed. Trans-esterification by using zeolite as catalyst is a good method to produce glycerol carbonate because of its reusability as well as a high conversion up to 100%. Nevertheless, this method has several disadvantages. Firstly, this method requires a mixing process. Mixing is another unit that makes the whole operation complex, and also it consumes capital and also increases energy consumption. Although zeolite can be reused by regenerating it, but the time used to regenerate the catalyst is very long, which is 12 hours. Calcium oxide is chosen as the best reaction because it has excellent catalytic activity in production of glycerol carbonate due to its strong basicity, low solubility in methanol, and readily available from nature or renewable sources that are rich in calcium carbonate and calcium hydroxide. By using calcium oxide catalyst in trans-esterification reaction, crude glycerol gives a perfect performance with about 95% yield of glycerol carbonate and 100% conversion of glycerol conversion within 90 minutes at the optimal operating condition. The diagram shows the block flow diagram. The entire reaction can be separated into pre-treatment and main reaction. In the pre-treatment section, the feedstock crude glycerol is introduced to the batch reactor along with phosphoric acid. Acidification reaction occurred in the reactor and a salt, monopotassium phosphate, was formed. Next, the output from the reactor will be sent to a separator to remove all the palmitic acids that consist in the crude glycerol as top product. Then the bottom output will proceed to the second batch reactor for neutralization by adding potassium hydroxide as alkali. Additional monopotassium phosphate was formed during the neutralization. The products are then sent to a decanter, followed by 2 flash drums. The decanter was employed for salt removing, while both flash drums were employed for water removal purpose. In the end, a high purity of estimated 96% of glycerol is formed and sent to the main reaction path. The product is sent to the mixer. In the main reaction, mixer was used to ensure all the reactants, which is glycerol and DMC, are well mixed prior to the reactor. The function of the heater is to preheat the feed up to the desired temperature, which is 95 degrees Celsius, before sending it to the batch reactor. In the batch reactor, glycerol reacts with the DMC to produce glycerol carbonate and methanol. Additional methanol is also introduced to the reactor as a solvent. The conversion of glycerol is assumed to be 100%. Next, all the outputs will proceed to the first flash drum to purge the entire methanol produced. The second flash drum was employed for unconverted DMC separation. The DMC that is separated is recycled back to the mixer due to abundant DMC were unconverted. This may reduce the cost of production and also reduce the waste produced. Lastly, the desired product, glycerol carbonate, was produced as the bottom product in the third flash drum, while the remaining components were purged from the top of the flash drum. The purity of the product is more than 90%. There are several heuristics applicable to this process. The first heuristic, drums are relatively small vessels to provide surge capacity or separation of entrant phase. Second heuristic, gas or liquid separators are vertical. Third heuristic, batch reactions are conducted in stirred tank for small daily production rates, or when the reaction times are long, or when some conditions such as feed rate or temperature must be programmed in some ways. The fourth heuristic, the optimized ratio with regards to selectivity, yield, reaction rate, and separation difficulties. The slide shows the base case flow sheet. This slide shows the plant layout. This slide shows the site layout.
I'll talk about material and energy balance. It consists of manual material and energy balance for selected chemical process and also simulation using available software for selected chemical process. Mass balance and energy balance is essential for every process. Therefore, mass balance was calculated by manually and also by using Aspen Plus. Besides, energy balance was calculated manually. This is the sample mass balance calculation. First of all, we have assumption that all reactions have 100% conversion rate. Sample shown below is the reaction between phosphoric acid and potassium hydroxide producing monopotassium phosphate and water. The feed for phosphoric acid are 209.6857 mol per hour, while feed for potassium hydroxide is 163.7913 mol per hour. According to molar ratio of the equation and also the assumption of 100% conversion rate, monopotassium phosphate and water have an output of 163.7913 mol per hour. On the other hand, unconverted phosphoric acid is 45.9844 mol per hour, and also unreacted crude glycerol is 1049.4775 mol per hour. As a result, the total output from reactor is 1422.9545 mol per hour. As we calculate according to method shown just now, we have 884.4063 mol per hour of glycerol carbonate produced, while result from manual calculation shown 992.6962 mol per hour of glycerol carbonate produced as a product. Diagram and table shown below is the simulation and result by using Aspen Plus. As what I mentioned, energy balance is also an important part when designing a process. Energy balance is calculated manually by using equation of enthalpy equals to heat of vaporization plus heat of formation plus specific component mass flow times specific heat capacity times temperature difference. If there are no temperature difference between inlet and outlet of unit operation, then temperature difference is zero, causing enthalpy equals to heat of vaporization plus heat of formation only. If there are no phase change, exclude heat of vaporization. Table shown below is heat of formation and heat of vaporization of component found from the internet. Next, I will show the sample calculation for energy balance. The unit operation for sample calculation is batch reactor 1. As we calculated the molar flow rate of all components in mass balance and also found specific heat capacity of component from the internet, we can tabulate it for the ease of calculating energy balance. By using general equation as shown just now, we can calculate change of enthalpy is equals to 8.1231 times 10 to the power of 9 kJ per hour. For chapter 4, I'll talk about process integration, optimization, and waste treatment. It consists of optimization of the process and design of waste treatment process. Heat exchanger network is designed to achieve maximum heat recovery, hence reduce operating costs. Table below is the temperature interval heat balance. The minimum hot utility is 1141.8721 kW, while the minimum cold utility is 0 kW. Besides, hot pinch temperature is 25 degrees Celsius and cold pinch temperature is 15 degrees Celsius. With the data above, grid diagram is drawn accordingly as shown. Heat transfer to C1 was calculated to be 112.8356 kW with temperature difference of initial minus final times with heat capacity of each component in C1. Assuming all heat is transferred to C1, H1 can be calculated by using simultaneous equation. Subsequently, final temperature of H1 after heat exchanger was calculated. The original utility needed for cooling H1 is equals to 1142.19 kW, while utility needed after designing heat exchanger is 1019.3411 kW. Therefore, energy saved from heat exchanger is 10.7556%. This is the new process flow diagram after putting heat exchanger. In this process, there are 5 main waste products that is to be concerned of are palmitic acid, monopotassium phosphate, potassium hydroxide, methanol, and water. Monopotassium phosphate is water-soluble salt, hence
Separation of salt from solution is either hard or in high cost through the usage of reverse osmosis. However, monopotassium phosphate has its value as a fertilizer or a food additive. Hence, monopotassium phosphate solution can be sold at a lower price to the processing plant that deals with monopotassium phosphate. In terms of wastewater product, it has little to no selling value. Hence, water itself is an abundant source of nature. Hence, the best way to handle wastewater product is to dispose it into wastewater storage tank for further handling. Waste potassium hydroxide produced is about 0.9025 mol per hour, which can be considered as low production. Therefore, excess KOH are to be disposed together with wastewater product into wastewater storage tank. Palmitic acids in small amount are of no value as there is no buyer. For methanol, it is not an option as the methanol for this trans-esterification process is of low purity. Hence, both waste products are best suited for biological treatment. Methanol and palmitic acid are going through aerobic reaction in which end product are carbon dioxide and water, which are environmental friendly compared to other type of biological process.
I will talk about 5.0 equipment sizing and cost estimation. For 5.1, I will talk about the design specification, and for 5.2, I will talk about the plant cost component, and for 5.3 and 5.4, I will talk about the cost estimation for auxiliary equipment and major equipment.
Design specification. In our chemical process of production of glycerol carbonate, it consists of batch reactor, clarifier, decanter, pump, mixture, heat exchanger, cooler, and pressure vessel. According to those considerations, stainless steel is chosen as the material of construction for the equipment. Stainless steel are steel alloy with at least 10.5% of chromium content by mass. The reason why we choose the stainless steel is because stainless steel is high corrosive resistant to acid, high strength, and ability to heal itself and low maintenance. In addition, the mixture that involved in pretreatment section was contain phosphoric acid. Hence, the material used for those equipment has to be resistant to acid. There are two types of stainless steel grade, which are grade 304 and grade 316. Stainless steel with grade 304 is the most common form of stainless steel being used in many applications around the world, and it mainly due to its excellent corrosive resistance. By comparison between 304 and other grade of stainless steel, it can withstand corrosive from most oxidized acid. Other than this, stainless steel with grade 304 is an economical and practical choice for most environmental, which is an important reason that we choose it as material of construction. Plant cost component. According to Aspen Plus, the volume of the batch reactor 1 is 0.231 meter cube. The volume can be used to calculate the radius and height. Hence, the height to diameter radius is 1 to 3. Thus, the radius is 0.1566 meter. So, the height is 0.9396 meter. The wall thickness of the reactor can be calculated by using this formula, which is Tp equal to Pd di divided 2Se minus 1.2 Pd. And finally, the wall thickness is around 0.006366. This table shows the design specification for batch reactor 1, 2, and 3. For pump 1, the horsepower of the compressor, which is called as WS, can be calculated by using this formula. According to Product and Process Design Principle 2004, the isotropic efficiency of centrifugal compressor is equal to 75%. So the compressor horsepower is equal to 435.782 HP. The power consumption PC can be calculated by using this formula. This table shows the design specification for the pump. For clarifier, the volume of clarifier is about 0.2311 meter cube. So the volume of the clarifier can be used to calculate the radius and height. And finally, the height is about 0.004596 meter. This table shows the design specification for clarifier 1 and clarifier 2. For decanter, the vessel of the decanter should be 95% full. So the volume of the vessel is needed to divide 0.95 and we will obtain 7.6737 meter cube. The length of the vessel should be 5 times of its diameter, which is L equal to 5D. So the diameter that we can be obtained is 1.2502 meter and the length is 6.251 meter. The depth of the interface between two fluids can be calculated by using this formula. This table shows the design specification for continuous gravity decanter. For the depth of the fluid, ZT is 1.1252 meter. The height of the interface between two fluids is 0.5626 meter and the height of the overflow heavy fluid is 1.0203 meter. For heat exchanger, the maximum velocity of the liquid Vmax can be calculated by using this formula. According to the stimulation result, the required area for the heat exchanger is equal to 0.02334 meter square. So the length of the tube can be calculated by using this formula, which is A equal to N pi DOL, whereas A is equal to heat transfer area, N is equal to number of tube, and DO is equal to outside diameter of tube, and L is the length of the tube. This table shows the design specification for the heat exchanger. For fresh pressure vessel 1, based on the result stream from Aspen Plus, the volume of the fresh pressure vessel 1 is equal to 359.496 meter cube. The volume of fresh pressure vessel is equal to pi r square h, and the ratio of length to diameter of fresh pressure vessels 1 is equal to 1 to 3. The wall thickness of the fresh pressure vessel can be calculated by using this formula. The necessary thickness to withstand wind load or earthquake is calculated by using this formula. Then the thickness of bottom of column in inch is calculated, which is 0.1377 inch. Then the average thickness of shell, and weight of the vessel is calculated by using this formula. This table shows the design specification for fresh pressure vessel 1, fresh pressure vessels 2, and fresh pressure vessels 3. For cost estimation for auxiliary equipment, the cost is calculated by using formula. This is a table shows the cost estimation for auxiliary equipment. The cost estimation of reactor, clarifier, and decanter were calculated by using Aspen Plus software. This table shows the cost estimation for the major equipment, which are batch reactor 1, batch reactor 2, batch reactor 3, clarifier 1, clarifier 2, and decanter. The cost for fresh pressure vessel 1, 2, and 3 is calculated by using formula. For fresh pressure vessel 1, the total purchase cost is 905975.3498 $, while for fresh pressure vessels 2 is 54920.2837, and for fresh pressure vessels 3 is 390602.2433.
Now I'll talk about the process control and safety. Under this chapter, I will discuss about the control system, piping and instrumentation diagram, and heads-up study. A piping and instrumentation diagram, PNID, shows the piping and related components of a physical process flow. is a foundation for the maintenance and modification of the process, which it is graphically represent. At the design stage, the PNID also provide the basis for the development of system control scheme. For example, hazard and operability study. PNID is drawn according to process flow diagram basis, but includes all the pipe flow direction, mechanical equipment, and control features such as valve. Engineers usually rely on PNID to construct safety, operational, and shutdown system by controlling the parameter transmitter, controller, and control valve on pipeline stream or equipment. This table has shown the PNID icons used in this process. The symbol, name, and function of the icons are listed in the table. The icons used in this process are including flow controller, flow transmitter, temperature controller, temperature transmitter, pressure controller, current to pneumatic converter, and control valve. Based on the PNID, we can see that every unit in this process has their own control system. First of all, flow transmitter is installed at the outlet stream of the reactor in order to detect the flow rate of the stream. If any overflow occurs, it will send a signal to the flow controller. At the same time, operator in duty will interpret the data by a computer system and regulate back to the desired flow rate. Then, a new signal is channeled back to the current to pneumatic converter, and the control valve will control the feed flow rate to the desired condition through pneumatic signal. At the same outlet stream, there is another temperature control system attached. When there is a differential value of temperature is detected by the transmitter, then the feed flow rate of another feed stream will be controlled in order to adjust the temperature. Therefore, the converter and control valve is attached to the feed stream. In addition, a pressure control system is installed at the pumps to control the pressure. A pressure transmitter is attached to the output stream of the pump for pressure indication purpose. When pressure of the stream is out of the range of the desired condition, then transmitter will send signal to pressure controller. Next, operator in control room may regulate back to the normal condition by sending the pneumatic signal to the control valve. Besides, the flow control system in clarifier, decanter, mixer, and the flash pressure vessel is the same with the flow control system in the reactor, while the temperature control system in heat exchanger and cooler is the same with the temperature control system in reactor. There are several deviations that may cause hazard in our process, which including high exposure of flammable chemicals, high temperature of reactor, overflow of chemical, incomplete reactor conversion, low flow rate, and process runoff. High exposure of flammable chemicals such as methanol may cause leakage in pipeline and cause fire accident or explosion. In order to prevent this occur, we have to make sure that the flammable chemicals are stored under confined spaces and no pipeline leakage issue. In addition, we also have to ensure that the flammable chemicals are not exposed to heat. Next, high temperature of reactor may cause high loading in pipeline and build up of pressure due to increased heat. The consequences of this deviation may cause temperature rise in pipeline and cracking may take place. Furthermore, explosion may occur in unit operation, therefore we have to reduce loading by controlling valve and handle with insulating glove. The third deviation is the overflow of chemical, which may cause excess flow rate of chemical. Thick chemical causes wastage, increasing capital, and may cause environmental damage. The safeguards of this deviation is install flow rate meter and a valve to stop chemical input if maximum volume of chemical involved in unit operation. In addition, incomplete reactant conversion will cause slow agitation, which may affect the purity of the product. Therefore, agitator speed meter can be installed to ensure that agitation speed is enough for reactant perfect mixing. Besides, low flow rate may cause malfunction of pump, which lead to low productivity and have to install a new pump. Lastly, undesired reaction condition of presence of impurities may occur if process runoff. This will bring a result of low purity of product. In order to overcome this problem, we can eliminate or reduce impurities contained before a process is launched. The standard operating procedure is a set of step-by-step instructions compiled by an organization to help operators carry out complex routine operation of every equipment or machines. SOP aim to achieve efficiency, quality output, and uniformity of performance while reducing miscommunication and failure to comply with industry regulations. The the startup and shutdown procedure of every unit in the production of glycerol carbonate are listed. For example, before start to operate decanter, you have to check the vessels of decanter to ensure it is dry. If any sign of corrosion occur, discontinue use until the corroded part has been repaired by a qualified service technician. If no problem, then can switch on the power supply. After that, the feed input can be introduced into the decanter. However, the liquids inside the vessel have to be ensured it is in a steady state or online condition. Lastly, set the desired operating condition and it is ready to use. On the other hand, when shutting down the decanter, we have to stop the feed from introducing into the vessel, then drain the remaining products. Lastly, remove undesired material from the decanter if any.
Now I will talk about chapter 7, which is mechanical design. In this chapter, it consists of detailed engineering drawing and equipment specification.
Detailed engineering drawing. The detailed engineering drawing of the equipment can be drawn by using AutoCAD software. This is the front view of reactor in 3D view, and this is the front view of the reactor from layout. This picture is show the top view of the reactor in 3D view, and this is the side view of the reactor in 3D view. For these two pictures, this is the side view of decanter in 2D view, and this is the front view of flash drum in 2D view. Equipment specification. This table shows the equipment specification of main reactor, decanter, and first flash drum.
Chapter of our project is the profitability analysis. In this chapter, I will discuss about the total capital investment and payback period or return of investment ROI. First of all, there are several statements have to be mentioned before the calculation. The first statement is the total fixed capital cost, including land value, is invested during 3 years of the construction period. Secondly, a straight line depreciation is assumed. Consequently, the plant will depreciate with a constant value in each year. Thirdly, the federal income tax is assumed to be 40% of the gross profit. Lastly, the working hours will be 8,400 hours per year, which is equivalent to 350 days per year. The grassroots capital GRC has been tabulated in this table. The base bare module cost of every unit has been calculated in the previous chapter. The sum of the bare module cost is about 1 million. By adding the contingency fee, it becomes 7.6 million. GRC is the addition of total module cost and auxiliary facilities cost, and it is 22.9 million. Now, we proceed to calculation of direct and indirect costs. Direct costs can be further categorized into on-site matters such as purchase equipment installation and off-site matters such as service facilities. On the other hand, indirect costs only consist of indirect matters, for example, construction expenses. By sum up of these two categories of costs, it is about 32 million. After added the GRC calculated, it becomes 54.9 million, which called fixed capital investment. Finally, the total capital investment is about 67 million after added the cost of working capital and startup. The total raw materials cost and the total product cost were calculated based on the price market of the materials. Based on the result of the calculation, the total raw material cost is about 1.3 million, while the total product cost is about 131.8 million. Next, the electricity fee is 8 cents per kilowatt. Hence, by multiplying this electricity fee to the works used by the equipment, we can find that the total cost of utilities is about 0.8 million. Now we proceed to the calculation of operational labours cost. In this plant, we assume to have 15 supervisors, 30 engineers, 90 operators and technicians, 30 material and product transporters, and 10 accountants. According to the salary market, the total annual cost for operational labours will be 9 million. The total land occupied in this plant can be classified into several sections. which including process units, auxiliary facilities, utility, storage tank, and others. By summing up all of this land occupied, the total land occupied is 11,750 meters square. In year 2017, the land cost in Malaysia is approximately $15 per meter square. Therefore, the total land cost is about $18,000. In order to calculate the annual profit of this plant, we have to first calculate the manufacturing expenses and also the general expenses. The manufacturing expenses can be further classified into direct and indirect expenses. The direct expenses have included the raw material costs, utility costs, maintenance and repair costs, operational labours costs, laboratory charges, and patent and royalties costs. The total direct manufacturing cost is 50 millions. On the other hand, the indirect expenses consist of local taxes, insurance, and plant overhead, and it is approximately 7.3 millions. The depreciation cost is assumed as 6% of the fixed capital investment, which is 3.3 millions. The general expenses are included the administrative costs, distribution and selling expenses, and costs for the research and development. The total of the general expenses is calculated as 4.6 millions. As a result, the annual gross earnings will be 112 millions by deduct all the expenses from sales revenue. However, by further deduction of the income taxes, the net annual profit is approximately 67.3 millions. This table has shown the total production cost by summing up all the variable manufacturing costs and fixed manufacturing costs. Based on the calculation, the total full production cost is about 27.7 millions per 1 kilogram of glycerol carbonate produced. So now I will discuss about the break-even point. The break-even point can be determined by using graphical method and also the calculation method. This graph has shown that the cost volume profit chart for the glycerol carbonate plant. As shown in the graph, the break-even point for the glycerol carbonate production plant is at about 19% of the production capacity. This is the calculation method to determine the break-even point. As a result, the production capacity is also 19%. Okay, now I will proceed to the total depreciation cost. The total depreciation cost is calculated by addition of direct permanent investment and contingency and contractors fee, which is 18% of the direct permanent investment. Therefore, the total depreciation cost for this plant is 107 millions. Return of investment (ROI) is the annual interest rate made by the profits on the original investment. ROI could provide a snapshot view of the profitability of the plant. In this plant, the ROI calculated is approximately 94%. Moreover, payback period is the time required for the annual earning to equal the original investment. It is also known as payout time, payout period, payoff period, and cash recovery period. By calculation, the payback period for this plant is 1.62 years, which is approximately 1 year and 7 months. An approximate measure of the profitability of a potential process or product that does take into account the size of the project is called ventral profit. It is used often for preliminary estimates when comparing alternative flow sheets during the process synthesis stage of process design. By calculation, the ventral profit of this plant is approximately 50 millions. Lastly, the annualized cost is a measure of economic goodness which does not involve sales revenues for products and is also used for preliminary estimates when comparing alternative flow sheets during process synthesis. In the production of the glycerol carbonate, the annualized cost is approximately 40 millions.
Lastly, I will conclude this presentation.
Although glycerol carbonate is a very promising product with high market value and various usage, its high cost of production makes its development rather slow, and it's only due to the reduce in glycerol's price that glycerol carbonate's research kick-started. Usage of calcium oxide as catalyst boosted the conversion rate to 100% with residence time of 90 minutes. In terms of costing, most of the cost goes to pretreatment, and the total production cost amount to 7.635 million. Overall, glycerol carbonate production of 93% purity is achievable as pilot scale, with production of 974.3626 mol per hour. Hence, development of glycerol carbonate production from pilot scale to full scale is hoped to realize in future.
The poster shown in the slide is a summarized version of our project, which consists of all the necessary information.